welcome. For very long time I have been wanting to do some videos, and now it's time. So I'm on a paternity leave I have been on like 1 month, and now I little bit start to have time to do something else as well. So I thought that I would pose a challenge to myself, and that would be to implement Maxwell equations in combined with TDDFT equations, so we would have the dynamics of the photons and the electrons, still in classical field theory, that is, and the density functional theory. We will use some simple functional or just even RPA. But to actually start implementing, I think for the 10 hours, I think we need like 5 hours to derive some equations or something like that, and then 5 hours to implement. And there might be some boring places if I'm like missing debugging for a sign error or debugging a code. So I think I will fast forward them to make it a little bit more user friendly. So I think we should start. Maybe we should start with an do we do 1D wave equation, or do we immediately start from the real thing? I think we can start from the real thing. So we can do this, that we can set the Lagrangian. So this is some very basic things, so that we just define that we define that the total Lagrangian is integral over space and of some Lagrangian density, which depends on R, and then the Lagrangian should depend on the wave functions, and these. So these are the Kohn-Sham wave functions, and there can be many of them. So like so, and then it can also depend on the scalar field. I think I would like to use phi as a sub psi is the wave function, and I want to use phi as a scalar field, and then also vector potential, all of which will depend on R. So let's see what it looks like now. And naturally the Lagrangian density depends on the same things. So and then we can start writing the Lagrangian density, and let's do two parts separate. So there's the coupling between the wave functions and the photons, so the Maxwell equations, and then there's the Maxwell equations, and then there's the TD Kohn-Sham equations. So I think that we will do the individual parts separately, and then in the end just couple them, just to make it a little bit easier, because I think it can get relatively tedious. So firstly, the Lagrangian, so we do L for freestanding for now the photon field, And this can be easily described as so the energy electric field is sort of like kinetic energy in this case, and the kinetic energy, the electric field energy density looks like this, and then the magnetic field is a little bit like the potential energy, and it looks something like this. Okay, and then I guess we can also define the electrons. So just to call it boringly L. And so we have something which looks, so we have the HXC of the density, so Hartree extends correlation potential of the density, and then we also have the kinetic energy, so sum over n. Then we have like just let's write it explicitly, psi n. Then we have the kinetic energy operator minus 1/2 Laplace squared, and phi n dfr, like so. And I guess we have also the occupation number here, and all of this corresponds to sort of like potential energy, so it will be minus. And then we also have the kinetic parts, which induces the Schrödinger equation, and that looks something like this, so it will be so psi star n, and then we make this one time derivative, and then we add imaginary part, and I think this will be very close to the actual equations of motion. I'm not sure about the Fn. Do we need it here or not? So that's it. So the Lagrangian L now depends on phi, psi, and psi star. And now we have to be extremely careful not to double count. So there will be HXC, where H stands for Hartree potential, and also the electrostatic potential will be represented in the Maxwell equations. So we do not want to double count that. Just to clarify, we're not gonna do density functional theory of the Maxwell equations of the photon field, so we don't have any photon densities or anything like that. We just have we just want to, like in the Hartree level, couple them. So we might get to that, but not in the scope of 10 hours. So, but for now, I will let the double count be. And then So then the coupling as such, so we can actually add the coupling already here. So maybe I will try to edit here. So let's try. So let's integrate over the density and the field phi, which will be the scalar potential. And this sort of acts now as an external potential. But let's see if, but there's from the free photon field Lagrangian, one also gets some nice results from the phi. So I think it would contain here the E squared, that would actually contain the Hartree energy. So this would be alright nevertheless. And then we also need to couple the vector potential. So I can always write the Matlab squared as P, and then we just implement minimal coupling, that's P plus A. So now this Lagrangian has the electronic plus the couplings. So like so, and that's squared. And the whole thing depends now on phi and A as well. And this is the momentum operator, so minus Matlab essentially. And okay, I think it starts to look sort of good. So now we just modify the free Lagrangian a little bit. So essentially we just substitute the basic definitions. So E is the vector potential, time derivative of vector potential, plus a gradient of a scalar potential. And that will be squared. Like so. So. Okay, so now, and we know that the B will be Matlab cross A. So, and that's also squared. So this will be Matlab times A. Like so. Okay. And now there's too much decrease of freedom, so we have essentially in space-time we have three components of momentum and 3 components of potential. But now we have changed into variables which are phi and a, and that's 4 components. So out of those components, one is the gauge freedom. So there's some gauge freedom between the phi and a, and we're going to choose a Coulomb gauge. So that sort of removes 1 degree of freedom, and we're left with 3 degrees of freedom, as there's 3. And then these 3 correspond to 1 longitudinal and 1 transverse. For example, in Coulomb gauge, the longitudinal electric field is always completely in the phi, and then A is completely transverse. So even A is a 3-dimensional vector. It only has it's only transverse, so it doesn't have that much information. Matlab.A is 0, so meaning for no divergence or no longitudinal components. So we're gonna choose that. And yes, so let's just call this the sum of the free and the sum of the free plus L. I mean, we could call it also L coupled or something. Okay. So let's start with the I'll just add some. We define the field Lagrangian and integral over the Lagrangian density. Which is given as a Lagrangian density of a free photon field. Then and the electronic Lagrangian coupled with including the light matter coupling. Okay. And then we just say that we will choose the Coulomb gauge Matlab CWFR. Since it will yield the familiar Hartree potential to the Kohn-Sham equations. So yeah, just to make it clear, this is not robust in full density functional theory of the photon field sense. It's just coupling to the environment. So at some point one could just say that, okay, fine, it's dipole-like, point dipole-like coupling or something like that. But nowadays we can calculate so big systems, and one actually could feel the wavelength effects already. So then we have to just, so this will be terrible, but then we have to just define the Euler-Lagrange equations. The Euler-Lagrange equations are given as. So essentially, the Euler-Lagrange equations mean delta L, the variations of L vanish, but which means that the variations of the Lagrangian with respect to the fields vanish. So this is with respect to wave functions. This is with respect to the scalar field, and then we need also with respect to Frog, with respect to the vector potential. So these are now these are functional derivatives. And then when you do a functional derivative of the L, which is functional, and the functional contains like time derivatives or spatial derivatives, then we actually get what is called the Euler-Lagrange equation. So we have to do some partial integration or something to derive it, and then what you end up with looks like this, that you essentially take partial derivatives of and then I'm only using the complex conjugate here. There's some degree of freedom how you choose this one, so I'm using the easiest possible way, I think. So what's wrong? Partial L pencil Frog. So dt Frog partial. I cannot figure out what is wrong. So the equation look, oh, now it just magically vanished. So and so this is the Lagrange equation, and now I actually, instead of so here I have the potential energy. I think I would rather write it as a kinetic energy density. So I would like to partially integrate. So there's p squared. There's two derivatives. I partially integrate, so the first derivative applies here and second here. And then we have reversal of the sign as well. And so I think it will be a little bit easier. So I will just so the p, it is minus I Matlab, and then I need to when partially integrating to get the kinetic energy density as an integrand. So this will be Matlab psi one half, and also Matlab psi, and then there's minus, and then there's I times I in there, and that's -1, but that is the one -1 which is cancelled by this one, so the -1 remains. So that's that, but now we have neglected, we have forgotten the other coupling terms. So we actually have other coupling terms. For example, there's the density, so sum over Fn psi n star times psi n is actually the density integrated with a squared. So we have actually term which looks a bit weird since it's it looks like this. So and so that's that. And then we also have the coupling term, and the coupling term is 1/2, and then we have the psi n psi n, and in here we then have minus I Matlab a of r and plus a of r minus I Matlab. So okay, it starts to look reasonable. So as one can see, it actually is quite a mess. So we have the Lagrangian equations, and we need to write them. So that was 1, and then we have the same equations also for the vector potential and the scalar potential. So we have it for phi. So this was for psi n, oh wait. So okay. So these are just the variational equations, and now over here we can just little bit copy paste to get equations of motion for phi and A as well. So phi whatever phi, and then for A so let's see. Okay, so these are the equations of motion. The fun part is that when this is done, we might actually go into the Hamiltonian mechanics, do a Legend transformation, and then derive the Hamiltonian equations of motion, because of some nice symplectic structure things. So what, as expected, I planned 5 hours for the equations. We're actually doing relatively well so far, but I haven't expanded this term. It's going to be terrible. So well, maybe it's worthwhile to look into the Schrödinger equation. That's the most familiar one, probably people know. So we take, so first let's take the time derivative term. So this one is the time derivative of psi star. So we will get psi n as the functional partial derivative, and fn, if that matters. Then it probably let's see. So, and then we take time derivative that, and then there's I. So we will take I fn psi n dot from the Euler-Lagrange, from this part of the equation. So that's like the first part of the Schrödinger equation now. So we have minus I psi n dot, like so. So we are, this is the Schrödinger equation part. And then there's lots of derivatives with respect to psi star. So for example, here. So we will have the minus IA plus A minus I Napla psi Fn. So I really am not sure about the Fn. It sort of seems weird here. I mean, we could just argue that they're always ones or zeros for now. Let's do exactly that. Because that's not the point. The answer is something trivial. Anyway, it just requires some thinking which I'm not focused on right now. So I think this was that. And then for example here we have n, and so we take functional derivative with respect to psi star. We will get psi from the n, so we will just get phi times psi from this term. And here we first we take functional partial derivative of exc with respect to n. We will get vxc, and then we take vxc. We take n with respect to psi star, psi dagger, and then we will get psi. So it will be vxc times psi. I mean, so this is how the Kohn-Sham equations formulate. So we can just write it immediately like so. So this is all the easy part. Like so. And then the coupling, the coupling terms. So these are actually, so officially this Napla applies. So I have a bad feeling that I might have been doing something wrong. So in the field Lagrangian part, but let's see. So let's first try the kinetic energy because it's the simplest one. So we are here. So we take the partial derivative of Lagrangian with respect to the Matlab psi star, and then so that's that one. So it will yield Matlab psi n half, and that one will be daggered, so we'll get minus 1/2 Napla dot Napla psi n, so that's the Laplacian. And then here's minus, and here's minus, so it will be plus, so it will be plus frac 1/2 Napla squared psi n. So this is actually working. So, and then there should be minus, so there was minus exc in the Lagrangian since it has minus the potential energy. And I'm not sure about the sign of this one. So this sign is wrong. So here we have I, and we have psi star, and then we have minus from here. So I'm just guessing that in the Lagrangian one should have minus I here. and then it reflects as I over here. So now when we move the VXE and the kinetic energy to the right hand side, they will have the correct signs of the kinetic energy and this one. And so the phi, the heart rate potential, or the longitudinal potential, enters here as well. So it's from this n with respect to psi star. And I'm missing 1/2 from this a squared, I see. Density integrand. So it does play a role, for example, in bond-motive force. But it's usually not that important, and usually in the electronic systems, since it's so small spatial dimension, it will just be a constant gauge shift, and usually it's gauged away. Okay, and then we are left with some of the annoying parts. So because here we actually I think there's no way of so I would almost like to claim that if we just take variable psi n normally without any Matlab dot things would work out just fine. So I mean, we are expecting actually minimal coupling. So we're actually expecting something like this. So left, right. So minus I Matlab. So this is just P plus A. But let's little bit think. Then is that what we will get? And I can just maybe immediately switch these to the right side, and then I can put the kinetic energy first. So now this actually looks like a Kohn-Sham equation, but except that I haven't actually derived this coupling. So for example, we take the derivative of psi star, and then whatever is in the right will remain. So we have PA plus AP psi n, and that's minus half. And then we should that's exactly what we will have, because here is psi, and these nablas, if you take them to operate to the right, they will operate to the psi without the complex conjugation. So it's exactly like so. Okay, so this one is correct now. So this one was the easy part. Then the tricky part is the Maxwell equations. So I wonder. So I have to write these open. And then derive the Maxwell equations for that. And then I wonder in which stage I need to apply the gauge. So the equations without the gauge, the equations of motion will be a little bit weird because the Lagrangian has degrees of freedom which do not change the physical symmetries, so they're so-called gauge symmetries in the theory. So we have to, at some point we have to use the Matlab.A is 0, the Coulomb gauge. I think there's no way of escaping it, that we just have to write this open. So it will be beneficial to do this. For me, I mean. So let's say to derive the Maxwell equations, we have to write open the free field Lagrangian. And so dot A, so it's dot A squared, and then it's dot A times Matlab phi. So these are all good terms into the Euler-Lagrange equation, plus then the Matlab phi squared. So these are now fine. This one is dot product, and then the Matlab times, so let's just curl, not curly curl, just to get it right. Fine. So this is some vector squared. It's Matlab times A squared, and the components of the vector is A z, and I'm gonna use a comma notation. So a z means the z component of A, but comma means that we take y derivative of that one, minus A y to z. This was one of the components of the vector. Then x to z, z minus a zx, and then y to x, a y to x minus a x to y. Okay. And maybe to be consistent, I can also do it like so. So this is actually a x to t squared plus a y to t squared plus a z to t squared. And dot, so, and this is a x to t times phi to x. Yeah, I think this will be beneficial in the end, because there's the Euler-Lagrange equations are gonna be relatively long maybe in this case. So ax to t phi x, a y to t phi u, z to t phi z. So and then finally the so this will be the 5x. Okay, and now there's a little bit tricky part here. We have to square this vector now, so it's gonna be even worse. So essentially these two terms will become 3 terms. So where was I? So yeah, I was expanding this and then z y z and minus 2. So x z zx yx xy. Okay, I think now it starts to look. So this is the free field thing, and I think there's no way to know unless we try. So we just take, I mean, maybe it will be, I mean, the phi ones. So we can see that there's no time derivative of phi. So it's actually not a dynamical degree of freedom at all. So there's a rather weird structure in the Maxwell equations. It's highly geometric. Actually, like, you can describe it as such that the second exterior derivative of some form is 0. So you can just use 3 characters to describe Maxwell equations in differential geometry in some suitable space and form. But so there's like 2 transverse dynamical modes, and then the longitudinals are not dynamical. but they're given by the source terms of density and current, and these are then again given by electrons. So the longitudinal electric fields are actually, the dynamics are driven, of that field are driven by the electrons, and then the electrons of course feel themselves, and that's how for example plasmons emerge, local field plasmons. And I think we have to just just need to start deriving. So let's see. First we need to take time derivative with respect to ax. So okay, so this is a vector equation here. So I think it will be worthwhile on vectorizing it as well. So we call this ax. And Matlab of ax. So now I mean, because otherwise the Matlab of A is a tensor, and then we have divergence of the tensor yielding a vector, and it's gonna be way too complicated because I don't have the experience. So it will be a lot easier if I just do it term-wise for now. Okay, now let's first look at Lagrangian equation for ax. Okay, so the explicit dependence, there's one, and that's this one. So this term is ax squared for the x part, and then you take it squared, you drop 2, this cancels this one, so you will get the electron density and A. That's a very, very weird term. That's so weird term that I don't like it at all. So, but I mean, we have to be sort of true to the equations. I can't really cheat. So I think there's something wrong with this term, maybe. But anyway, that was the only dependence. Then time derivatives. So I mean, maybe we can write this even simpler. So using the comma notation. So this one, the dot is just x comma t, and the nabla we can just change that into 3 parts, vectorize that also, or like serialize that also, and it will be ax of x, like so, and then we just add the rest of the partial derivatives as well. So And so we search for a partial derivative of ax comma t. That's here. And so we get epsilon 0 axt. And then we get the new time derivative and minus. So I think that will end up as second time derivative of, okay, I can use my new notation, axtt, and that makes sense. And then there's like epsilon 0 in here. And okay, so it's already second in time derivative, so it starts to look like a wave equation, which is what is needed. Then there's axt here, so that will be so I think the half is too much here somehow. I think I have forgotten. So it's a plus b squared, so the ab term is twice. So I think this half has to go. And I think I have repeated the mistake somewhere here as well. Not necessarily. Maybe not. Okay. So now we get epsilon 0 phi and x. So we get minus, then we get phi or x and epsilon 0, and then we take time derivative t, so that we get phi xt. Okay, I think I remember that that's also expected. Then so these were the time derivative parts, and then we take ax derivative of x, partial derivatives, there's none. Then we take xy, and so there's 2 xy's and 1 over 2 mu 0. So this 2 cancels this 2, and when you take the second derivative, this drops and cancels. So both of these drop, cancel this, and then you have minus here and minus here. So for this one, we will have 1 over mu 0. We have axy, and so that minus and that minus cancels, and then we have this derivative here, so we have xyy, and then this one will have different sign. So we have plus 1 over mu 0 this will be then xy, so we will yield a y x and y, and then this term, so we search for xz, So a x z squared, so it will yield this kind of thing, x z z, so that one, and then plus, so there's the x z here, so we will get a zx, a zx z. Okay, so I think this is the Euler-Lagrange equation. So this term is something wrong with that. Otherwise it looks okay. Then we need the same equation for all the coordinates. So maybe we can already a little bit guess. So at least it's always a y, like so. But then for the magnetic field, I think one just has to do the math. So it's always a y now. So for the magnetic field, so we have a yx. So we have here a yx. So it returns a xy. And then we take with respect to that x, so a xyx, a xyx, and then we have the ayx, we had it also here, we have the ayx. So this will give a yx or x. And then y derivatives don't exist. Then we have z. So I have a y z. A y z will be a zy over z, and then we have a y z squared, so we will have a y z or z, wait, it's the same, so y z z, and so this y z was n z y z. Let's see if it's in any way symmetric. So then I'm gonna just guess the one more equation. So z, and it seems always that we have the Matlab. So we have xx and z. So I think this one, the final equation for z, will have xx and yy. of the z, and then we will have, so in the x, for the minus terms, we have x, so with y and z here. So then we have so this is z, so we have x and y, and one of the derivatives needs to be, so wait, so x y of z, and then we have x and y over x and z x and y and z y. So this is a very rough estimate. So then we notice that there's something in common. So there's always y and z. So there's almost a Laplacian. So I'm gonna add. So firstly, I'm gonna group the terms. So like so, and like so. And like so. Then I'm gonna add and subtract the missing Laplacian term. I'm sort of cheating because I know that the equation of motion eventually will have a Laplacian. So I'm adding here minus z with z, and I'm also subtracting it like so. And same here, then I will add y to y and subtract it also, and this I will copy somewhere over here, and same for here. So we have so I will have x, and then same x will be copied somewhere over here. And now, so we see that this is minus 1 over mu 0 Laplacian of ax here. And then I think I might be, so there's, so how many terms? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. So it remains that you have ax, you have x, y, and z, and then you have everything with respect to x. So I think I also remember this from somewhere. So essentially, let's just write it open. So we have a second derivative of a, like so, minus epsilon 0 nabla phi and dot time derivative, and then we have the n, the weird term. This is what I don't understand, that how the density acts as a source term. So yeah, I think that usually the fields are so slow that people neglect this. So I think like I haven't ever seen this. I think that's because people always neglect it, I'm guessing. So one would have to go into like region where there's pair production or something like that, maybe. I'm just guessing. So now we have frac 1 over mu 0, and then so then we have the nabla a, nabla squared of a, and then the crux is that we have plus 1 over mu 0, and then we saw that this looks like gradient of the divergence of the vector potential. And then we're still missing something, since we are missing the source terms from the current. Yeah, I think this is sort of starting to look like Maxwell equations. So we have the minimal coupling over here, and so we have, for example, A, and this A then becomes the momentum operator. So it's supposed to So I think that when I take a functional derivative of this expression with respect to A, firstly we get minus I nabla, and then we get here a term which still to be operated with nabla, but I could choose that the nabla operates to the left if I, for example, like I can just do that, I think. So it operates to the left, and then I'm left with A again. So I think it just, what it yields, there's 1/2, it just yields the probability current density. One should probably, in correct units, one probably should have electron charge here. So as a bold assumption, I'm gonna write J here. Well, not here. but to here. I'm allowing at this stage some sign errors, I guess. So I'll just Google Maxwell equations in Coulomb gauge vector potential. Vector potential of the Coulomb gauge. So Maxwell equations. So there's mu0 in the J, but that's because there's 1 over mu0 here. So we would need to multiply with mu0. I mean, we can just do that. So here becomes mu0, and here, and this one cancels, and this one cancels, and this one gets the mu0. So we have Nabla squared A. So then we have minus of the, so let's make sure. So we have minus second derivative and Nabla squared, and here we have minus and minus, so there might be something wrong. So here's minus Nabla, and there's one minus from here. So yes, so these signs are wrong. So no, wait. So there's one minus here and one minus here. So that should cancel. So all the signs are wrong here. Okay. I think I can do this. So plus, 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 minus, minus, minus. Plus, minus, plus. Okay, and then the minus mu0 Nabla squared plus and minus, and then it shall reflect here that the Nabla squared will be plus. Okay. Yeah. So the epsilon 0 mu0, it is same as 1 over c squared, and that's minus. So that's correct. And then we have Nabla of phi dot epsilon 0 mu0, Nabla of phi dot epsilon 0 mu0, and minus sign. That's also correct, it comes from here. Then we have Nabla dot A with minus sign. So this I forgot to change. It's correctly minus here. And then we have equals minus mu0 j. So we have it on the left side, so plus mu0 j. Okay. So we have derived the Maxwell Kohn-Sham equations. That was very instructive. I think one needs to do that sometimes to convince oneself. I mean, you can read all you want about some equations, but eventually you will start learning less unless you actually go deep into them. So that's 1 hour 25 minutes, and so we are not completely done yet, as we need to utilize the Coulomb gauge, and it's very handy in the sense that we already have the Matlab.a here. So we can just say, or in Coulomb gauge, we just remove the whole term. Like so. So as one can see, there's absolutely nothing related to density here. So either I have done something wrong, or then it's usually neglected. So I don't really know. But that's not the main concern. In the end, I will anyway neglect it. Then we need to derive the equation, Lagrangian equation for the phi. So we only have n and then derivatives of phi, spatial derivatives. So we take, for example, so it will become the divergence of Matlab phi epsilon 0. So the Lagrangian equation for phi becomes, so Matlab phi, and then from Lagrangian equation we get Matlab c dot Matlab phi, and then we have the epsilon 0, and then we also have phi over here, which will yield minus n. So we will just have minus n, and I can just remove the minuses, and then I can just put n to the other side, and then I can just divide with the epsilon 0. And then this is just the Laplacian. So, and then we can just, so Matlab.e, which is Matlab phi equals rho divided by this one. So I wonder, did I miss a sign error somewhere? I might have missed. So let's just let's see. So this one here is potential energy, so it's minus. So we will have minus n in the Lagrangian equation, and then we will have from the free part, we will have this one, which is then it's in the kinetic part, meaning the electric field part, so it's plus. And then it will be minus. So both of them will have minuses. So I wonder, is this just my sign convention of some sort? So, and then one more. Epsilon 0 AXT. So phi or x. So we will get epsilon 0 Matlab dot a dot. Okay. I think I need to do it all over again. Let's just do it from the scratch. So firstly, we will get minus n. So this is so from this term we will get minus n, and then we won't have any time derivatives, but we do have these Laplace here. So where do we have them? We do have them here and here. So this one, the 2 will cancel this one. We will have epsilon 0 and that one, and then we will have second derivative of that one. So, and here we will have the 1 minus. So minus epsilon 0 Laplace squared. So minus epsilon 0 Laplace squared a. Sorry, phi. So this is now looking like the Poisson equation. And then we will have one more term over here. So derivative with respect to this one yields AXT. So that's like minus epsilon 0 dot a. And divergence of the, so this divergence comes from the divergence of the Lagrangian equation. And I can also put the divergence in here. Like so. So, and this one then this one then in Coulomb gauge, since divergence of A is 0, yields that the Matlab phi equals n divided by epsilon. So the fact that I have the wrong sign, I don't know. Should I have but if I would have chosen the phi, so I have chosen this, the sign of this here, the phi. But if I have chosen it wrong, So that might be why I get the different sign from here, or just how the electric field is defined. No, wait, there is a minus. Okay, now I think I have exactly the right equations. Okay. Now except for this one, this is I'm not so sure about. So but so I wonder, is now time to start to implement this. There's there's of course lots of symmetries, and for example Noether currents and so on. One important part is that one needs to so there's two source terms in the Maxwell equation, the density and the current, so that's 4 terms in total, and they need to fulfill the continuity equation as Schrödinger equation does, and that way that also keeps the Maxwell equations like covariant when they do that. So there's like implicitly one more term to be considered. So there's something about the currents, I think. So I think this one minus this one equals the transverse currents. So let's see. So, and I think that's also what is related to the what I just said previously. So the Schrödinger equation fulfills the Schrödinger equations conserve the charge, and thus there is a continuity equation. So we have the divergence of the current. It might be fun to do better to derive the current from the minimal coupling. So this should equal to the time derivative of the density. So equation of continuity. This is something. Oh, so yeah, it's like so. So now we can see for example here that we have, for example, the so I wonder what if we would, so there's Matlab.j. So if we would take Matlab.j, let's here, And then we would take Matlab dot here, so this would become the Laplacian of the potential. Then we can utilize this equation. It would be 1 over epsilon 0. And then there's the dot, so it becomes dn dt. So these two cancel for the longitudinal part or something like that. It's worthwhile doing it more properly. So how do I say it? We know that transverse, that only transverse currents couple the vector potential in the Coulomb gauge. And how do we so I mean, we can always do the Helmholtz decomposition, but I think there has to be a better way. So, I mean, we can do the Helmholtz decomposition of the current. So the current becomes J minus squared Matlab J plus Matlab. So this one is the longitudinal part. I think it's supposed to be dot. So divergence of the current yields minus dn dt. And then with that we can solve the Poisson equation, and we can then take again the electric field in case of source term, but now it's the time derivative, so it's the current change in the electric field. Let's see. So now we essentially, so this is the transverse current, and then we focus on this term here. So let's just put this in the Coulomb gauge equation. So we take this equation and then we substitute the J with complete identity. So nothing happened yet, then we can substitute the Matlab.j with the continuity equation, so minus dn dt. So there's Matlab.j dot, so I will substitute minus dn dt. And this depends on r. And then I can use the Laplace equation. So we already in Coulomb gauge we know this. So we take time derivative of this. So Nabla squared phi dot equals 1 over epsilon 0 n dot. And now we divide with the Nabla squared. So that becomes like the Coulomb kernel. So we get that phi dot epsilon 0 equals Nabla minus 2, and it exactly, the epsilon 0 becomes to the left hand side, so it exactly cancels that one. So I wonder, it's probably worthwhile to do one more step. Where we explicitly use that we substitute this one with Nabla squared, so the minus n dt. This is what we substitute with Nabla squared dot phi, and then there needs to be epsilon 0. And this one is cancelled, Matlab, and mu 0 comes here. So eventually this one, so this one cancels the longitudinal part of the current, and only the transverse current remains. So we call this one the transverse current, and this one the longitudinal current. This is called the longitudinal projection. So, and then I guess this stage it's probably worthwhile to put the current as a source term to the right hand side of the equation. The baby and mother are sleeping in my study, so I'm in our bedroom, sitting in a bed. and leaning to the wall. It's not the most comfortable setup. Anyway, so let's in conclusion, the equations of motion in Coulomb gauge are. So it's this one. And then we have the Coulomb gauge. So when we're actually coding this, so this is just the arbitrary potential, so we don't actually do anything. Oh, I see immediately problems. Or do I? So actually, there might be some problems. But let's just copy these equations first. So this is the Kohn-Sham part. Yes, I think so. Looks about right in many ways. So sure. I think it's correct. So this one surely is the Coulomb potential, is the Hartree potential, and this is where it's applied. I was worried about the sign. So factor of 1/2. So here we see that there's the phi times n. So this is actually too much in some sense. So it's actually twice the Hartree energy, if you think about it, because phi is the Poisson solution to density n, and usually you have 1/2. So if there wouldn't be any coupling to the Maxwell equations, there would be 1/2 for the Hartree energy. Now on the other hand, you have here in the free part, you will end up having like phi squared in this and Matlab squared, and here's 1/2. So this actually now cancels part of this, because the phi will actually be linked with n. So I can just change one of these phi's with n, and it's a Poisson solution, and so on. So I think it's sort of relatively okay. So we definitely, so I have probably used some mixed units. This Schrödinger equation is definitely in atomic units. So epsilon 0 is not part of the atomic units at all. So I would like to put this in atomic units now, so that I can actually implement it. So this is 1 over speed of light, and speed of light is 137, so it's 1 over the fine structure constant. So it's 1 over c squared, and c is 137, so it's actually alpha squared, like so. And then the epsilon, so in atomic units 4 pi epsilon is 1. This means that epsilon is 1 over 4 pi. So this epsilon, 1 over 4 pi, 1 divided by epsilon is then 4 pi. So this one is just 4 pi. We can maybe check that. So let's say Coulomb Poisson equation in atomic units. Let's see if we have Poisson equation in atomic units. Yes, you have the 4 pi. Fine. And yeah, okay. So I think that's pretty much it. And I think now it's a good time to stop the video and then start again with the implementation video.